Okay, so today we're going to continue and we're going to talk about collisions. So finally, things are going to start hitting together. So, this happens a lot when you just make a football example real quick. So you have a person, running fast, and then they're going to get tackled by this person who's going this way. If this is to scale, which way are they going to wind up going? Well, momentum's going to be conserved, and it looks like that this person has a big momentum, so the final product is going to be some blob of people going this way. So in this case, they stuck together, but I'm jumping the gun a little bit. Let's see what we can do. Let's go take a look at this. So the basics of collisions: momentum is always conserved. You can always use conservation of momentum, and it's going to be a really helpful thing. Now, kinetic energy may or may not be conserved. And this is just because energy can be lost as heat or sound. It deforms things. So like if we'll have this person over here, and this person throws a chunk of Play-Doh. That's Play-Doh, not a rock. And you wind up with something that looks like this person, and then this Play-Doh kind of deforms. Yes, it turned green. You lose energy to that deformation. So total energy is going to be conserved, but the kinetic energy may not be. But momentum is always conserved. So there are two types: inelastic, where they stick together. This would be that Play-Doh example we just talked about. And then perfectly inelastic. So in inelastic, things bounce. This would look like you have a ball going this way, you have a ball going this way. They will hit, and then they just bounce apart from one another. So that's perfectly inelastic. Today we're going to focus on, when they bounce, that's elastic. Think of rubber bands. Okay, and that was me moving out of the chair and kind of falling. So sorry about that noise. So in a perfectly inelastic collision, momentum is conserved, kinetic energy is lost, it goes to heat, and we're going to do an example of this, which is a car crash. Well, I know, it's kind of sad. So let's say that we have, a truck going this way, a car going this way, and at the end, you're going to have this mass, and it'll eventually go this way. So again, we're always going to start with momentum initial equals momentum final. So we look at this. What's the truck's momentum? So this would be mass of the truck, velocity of the truck initial, plus mass of the car, velocity of the car initial, equals mass of the truck plus mass of the car, because they're going to stick together, times this final velocity. In an inelastic collision, both objects are going to have the same final velocity, because they stuck together. So we're going to move this over here. We're just going to divide, so we get mt vt initial plus m car v car initial all over mc plus mt. So we plug in the numbers. You get 1,800 kilograms, this is the truck's part, times 15.0 meters per second, all over, plus 900 kilograms, in this case it's negative 15 meters per second, because it's going the other way, all over 900 plus 1,800. So if you work this out, you find out that your V final is going to be equal to 5.00 meters per second in the positive direction. And that is how you work a conservation of momentum problem in one dimension. At least an inelastic collision. So now, what we're going to do this example of a ballistic pendulum. So you have to break this into two parts. So what's going to happen? This right here, bullet hits the block, gets stuck, gives the block some initial velocity, and it flies up. So for part 1, you get m1 v1 plus m2 v2. All these are initial. We notice that block isn't moving, equals m1 plus m2, make that a better plus. And if you can hear in the background, that is my cat. So she's not so happy. And then we're going to solve for this. So we get the mass of the 1, that's the block, times the velocity of the block initial, over m1 plus m2 equals your final velocity. And if you plug this together, you're going to get that your final velocity, using the numbers we provided, is going to be, well, you can solve for that. And I'll actually leave that to you because I want you to take a look at it. And then, let's assume that this V initial is 1,000 meters per second. Then you will plug this into part 2 to find out how high this block goes. Now this is just a conservation of energy equation. So we know that no non-conservative forces, so you get Ke at the beginning equals potential energy at the end. So this would be m1 plus m2 GH equals 1 over half m1 plus m2, and I'm going to have to write it over here because I ran out of room, times that final velocity from part 1 squared. Now you could also go about this using the initial velocity of the bullet to figure out how high this goes, but in this case I just wanted to show you that you could combine these two things. And I will leave this as an exercise for you to do. Hopefully that makes sense. Please email if it doesn't. That was our lecture on inelastic collisions, and I will talk to you later.